Hello everyone, good evening. So let's start the lecture of this week based on AC bridges. So we will solve couple of problems based on AC bridges. Okay. So let me take the first problem here. One inductance and resistance are connected in parallel, and in other branch, another inductance and resistance are there. Okay, and here deflection will be measured with the help of galvanometer. And in another branch, other resistance R3 is connected, and in last or fourth branch, another resistance R4 is connected. Okay, and they have been fed with the supply with an AC supply here. E L1, R1, L2, R2. Okay, and these values are given as L1 is equal to 150 millihenry and L2 is equal to, again, same value. Now R1 is equal to 20 ohm and R2 is equal to 10 ohm. Okay, so we need to find out the angular frequency at the balance condition. Okay, so we need to balance the bridge here and then we need to find the angular frequency. So how to find it? Let us proceed. So at balanced condition, what will happen that impedance of Z1 and Z4 magnitude Z1 and Z4 should be equal to Z2 and Z4. And other thing is that angle of theta 1 plus theta 4 should be equal to theta 2 plus theta 3. Okay. Now, so start it with the real and imaginary combined. So start with the entire impedance in vector in polar form. So uh, Z1 is equal to R1 parallel with J omega L1. Okay. Similarly, Z2 is equal to R2 plus J omega L2 because both are connected in series. Z3 is equal to R3 and Z4 is equal to R4. Okay. So at balanced condition, what we will do, Z1, Z4 is equal to Z2, Z3. Now, Z1 is R1 into J omega L1 divided by R1 plus J omega L1. Okay. And Z4 is equal to R4, Z2 R2 plus J omega L2 into R3. So now we have one job here to segregate the real terms and imaginary terms. So if we can segregate here, then we will equate real terms to real terms and imaginary terms to imaginary terms. Okay. That way it will be easier to solve for us. So now R1, R4, J omega L1 divided by R1 plus J omega L1 is equal to R2 R3 plus j omega L2 R3. Now, if we simplify it further, R1 j R1 R4 omega L1 is equal to, while taking this term on the right hand side and multiply it, you will get R1 R2 R3 plus j omega L1 R2 R3 plus j omega L2 R1 R3 plus j square will be minus 1, so it will be minus 1 minus omega square L1 L2 R. Okay, so we have a pretty bit simplified it, and now what we can do, we can equate the imaginary terms, because only two terms are there, or what you can do, you can equate real terms as well, isn't it? So to equate imaginary terms, what we have to do, we can you know take R1 R4 omega L1 is equal to, imaginary terms on the right hand side are omega L1 R2 R3 plus omega L2 R1 R. So here you cannot get any solution by equating imaginary terms. Because omega and omega will be cancelled out, and you are not going to get any solution here. So now next part is we can equate real terms. So real terms are R1 R2 R3 is equal to omega square L1 L2. Okay, so finally what, and R3, yeah, so here R3 and R3 will be cancelled out, and we will end up with omega is equal to R1 R2 divided by L1 L2. Okay, so this is how we calculate frequency of this bridge, where we can uh, you know lead lead with couple of equations or couple of solutions, but we have to take care of how to equate real and imaginary terms separately. Okay, so I hope it is fine. Now another thing is asked here: what will be the value of R4 by R3? Okay, so value of R4 by R3 will be nothing but the value of Z1 by, sorry, R4 by I3 is equal to Z2 by Z1, isn't it? From the bridge, you can see it will be equal to Z2 by Z1. Okay, and Z2 is equal to R2 plus J omega L2, and Z1 is equal to nothing but, you know, R1 plus 1 by, sorry, R1 plus 1 by R1 plus 1 by J omega L1. Okay. Now what we can do, we can further, simplify it, R4 by R3 in real and imaginary. We will multiply them first. So R2 by R1 plus j omega L2 by R1 plus R2 by j omega L1 plus omega L2 by omega L1. J and j will be there. They will be cancelled out. Okay. So if we want to find out R4 by R3, then we must focus on only real term. Okay. So real terms are here. These two are imaginary terms, and these two are real terms. So we can safely say that R4 by R3 is equal to R2 by R1 plus L2 by L1. So this is how we find the value of R4 by R3 from this bridge. Okay, so R4 by R3 is nothing but is equal to Z2 by Z1. Okay, and finally since R4 and R3 both are real, so we need to equate them with real term only. Okay, so I hope it is fine. Okay, any question on that? So let's move on to the next part of this problem. So there is a statement and we have to uh, predict whether it is true or false. So from this bridge, whatever was provided in question number 1, we have to tell that given any arbitrary set of values of these parameters L1, L2, R1, R2, R3, R4, it is always possible to obtain a balance by adjusting only the frequency of supply. So basically the statement is with only tuning the frequency of supply, we can balance the bridge. So this is the statement. We have to tell whether it is true or false. Okay. So see, in this is AC bridge. Okay. So here frequency is important. Yeah, frequency is one parameter, but what other parameter on this bridge balancing depends. So that parameter is also angle, right? So here you see if angle will change, then we have to tune both of them simultaneously, or we have two dependent parameters to maintain this bridge balancing. Okay, so that is why this statement will be not true that with only tuning the frequency of supply we can balance the bridge. We have to also tune the either magnitude or angle. So that is other factor on which balancing will depend on. And another statement is, or another logical reasoning question is like, the bridge can be balanced if the supply waveform is, so this supply waveform, we have to you know tell that on which supply waveform this bridge can be balanced. Like there are a couple of AC signals, we all know, like sinusoidal is, ideal kind of waveform. Then the square waveform, that is also an AC waveform. Then triangular waveform, or any periodic function, or half wave symmetric. So let me write down the options. Sinusoidal, a square, triangular, half wave, symmetric waveform, and any periodic function. So which type of supply waveform should be there to maintain this bridge in balanced condition? Any idea do you have? Which kind of supply should be there to maintain this bridge in balanced condition, and why is that? Also, that would be an interesting point. So do you think that if we, provide a square waveform or triangular waveform, this bridge will be balanced? Niranjan, are you there? Could you please let me know?
Yes, sir.
Yeah, so with a square waveform supply or triangular waveform supply or any kind of sinusoidal or AC supply, which kind of supply should be there to, maintain this bridge in the balanced condition? So let me start with a square, okay?
Your sign.
So pure sine, exactly. Yeah, that is correct. Pure sine. And why? Could you please throw some light on that? So let us assume we have a square waveform. Okay, it will have, if you further derive the Fourier series of this square waveform, you will get, sinusoidal A1 sine omega t plus A3 sine 3 omega t, and so on, right? So there will be multiple frequency, harmonic frequencies that will exist with this kind of waveform. Okay. And in sinusoidal, only we have single fundamental frequency, that is omega, right? So in sinusoidal, we will have only this component. But in a square waveform consists of all those harmonic components. So it is very difficult to maintain this circuit in balanced condition with all other frequencies. So if you try to maintain this circuit in the balanced condition for couple of frequencies, but it is impossible to maintain this circuit with all the harmonic frequencies. So that is why sinusoidal waveform is always preferable in AC supply or in AC circuit. So we do not need to bother about other harmonics, and we can maintain this bridge in the balanced condition. Okay. So that is why a square waveform will also not be desirable, triangular also not be desirable, same with half wave symmetric or any periodic function. Only sinusoidal will be preferable in the case of balanced circuit. Okay, any doubt there? So if not, then let's move on to the next problem. So next problem is based on, again, another high voltage AC bridge circuit in which one branch has a capacitor, other branch has series combination of capacitor and resistor, C2 R2, or you can say any unknown as well. And here galvanometer deflection will be measured. And the third branch will have C3 in parallel with R3, and fourth branch will have R4. Okay, and it will be fed with a supply, AC supply, sinusoidal supply. Okay, so values are given here. C1 value is 1 microfarad. C2 is, sorry, C3 is 900 nanofarad, which will be 0.9 microfarad. And R2 is, or rather R3 is 170 ohm. And what else is given? R4 is also given. R4 is given as 400 ohm. Okay. And here we need to find out the value of C2. So this must be Steiner's bridge, which you might have studied in the lecture, where high voltage bridge, you know, where the desirable voltage drop across this branch is very less. It should be almost close to zero drop from this V4. This V4 should be close to zero in high voltage circuit, and most of the voltage should drop across these two parameters, or you can say elements. Where why that? Because we have to tune these two elements in such a manner so that during any short circuit condition, these, because of this resistance, it should not impact this circuit. So that is why Steiner bridge is very important. So we need to find out the value of C2 here. Okay, so again, okay, some message is there. Okay, okay. Yeah, so how to proceed with the calculation of C2? So again, we will do the same thing. We will multiply Z1, Z4. We will do Z1, Z4 is equal to Z2, Z3. Okay. So now
Okay,
what
sir.
we can, yeah, hello. Yeah. So we can multiply this R4 and C1 here. We have the value of R4. We have the value of C1. So we are almost done with Z1 and Z4. So Z1 will be 1 by J omega C1 into Z4 will be R4. Now, Z2 and Z3, they are a bit tricky. Okay, so how to deal with them? So Z2, let us first write Z2 is equal to R2 plus 1 by J omega C2 into multiplication of Z3, which is nothing but R3 parallel with 1 by J omega C3. Okay, now it is better if we take them on this hand side so that it will simplify our process. So R4 by J omega C1 into what we can, how we can write it? R3 is there, so that will be like admittance. So 1 by R3 plus J omega C3 is equal to R2 plus 1 by J omega C2. Okay, now we are good to go. We can simplify it here, J omega C1 R3 plus R4 J omega R4 C3 divided by J omega C1. Now we can equate them with R2 plus 1 by J omega C2. Now again we will do the same thing. We will equate the real terms with the real terms, both on the left hand and the right hand side, and imaginary terms with imaginary terms. So first thing is that j omega will be cancelled out here, and we will left out with, you know, real term, that is R4 C3 by C1 is equal to R2. So here we can know the value of R2. So R2 will be this much. Okay. Now we need to find the value of C2, right? So now we can see from the imaginary terms, can we identify the value of C2? So yeah, here this is one imaginary term and here this is another imaginary term. So we will equate them both. 1 by j omega C2 will be equal to R4 by j omega C1 R3. Here j omega and j omega will be cancelled out, and we will end up with C2 value is equal to C1 R3 by R4. Okay. So this is how we simplify this AC circuit, whose balancing is a bit tricky, but we can do that anyway. And we just need to take care to segregate it very conveniently with AC real terms and imaginary terms. Okay. Is there any doubt in this part?
No, sir.
Okay, great. Thanks. So let us move towards the next problem. Yeah. So we need to find the dissipation factor of this capacitor, which we just found out, R2 and C2 branch. So we need to calculate the dissipation factor of this branch. Okay. So you might have gone through the lecture. So what is the dissipation factor? Do you have any idea about that?
1 by Q, sir.
1 by Q. Yeah, exactly. So dissipation factor is, not inversely proportional. It is equal to
Like
inverse of
omega
quality factor.
C.
Yeah. Yeah. And quality factor is nothing but tan theta. Okay. And tan theta is nothing but imaginary terms divided by real term, isn't it? So
Real.
since we have to find out in this branch C2 and R2, so we can draw the phasor R2 and uh, K omega C2, and we will have some resultant towards, and we can find out this will be the theta angle. And here, from here, we can write down tan theta is equal to nothing but J omega C2 by R2, isn't it? And if tan theta do we know, then sorry. It should be X2 by R2, and X2 is nothing but 1 by J omega C2 into 1 by R2. Okay, so this is X2 is equal to 1 by J omega C2, like that. Because capacitor is, inversely dependent on the impedance or reactance. So that is why it will be like tan theta will be 1 by J omega C2 R2. And now we know the tan theta, we know the quality factor. Okay, we are done with quality factor, but we need to provide the value of dissipation factor, which is inverse of quality factor. So dissipation factor will be equal to J omega C2 R2. So this is the value of dissipation factor. I want to know whether, dissipation factor is better for the circuit, or it is, negative parameter which we want or which we do not want in the circuit, or the higher or better, or the lower the better? What do you recommend?
Lower, sir.
Yeah, exactly. Dissipation factor should be lower in the circuit. Okay, dissipation factor means, your energy is getting dissipated in form of heat, and hence the efficiency of the circuit will be very poor. So that is why the lower the dissipation factor, the better. Okay.
Okay, sir.
Now the last part of this problem is, see, the term which I was explaining, that why this Zener is designed like that, that majority of voltage get dropped in this variable branch. So that concept we are going to see with another problem. Okay. So here it is being said that if supply voltage is 4 kV, okay, if supply voltage is 4 kV, okay, supply voltage is 4 kV, and frequency is also given 60 hertz. Now we need to estimate the voltage across the variable or controllable arms at balancing conditions. So we need to find out this voltage V2. Okay. Since V is 4 kV, here also it will come out to be 4 kV, and this will be ground. So it will be 4 kV. We need to find out the value of V2. So can we do that easily? I hope so.
Yes, sir. Yes, sir. Sir, I
Exactly.
have
We
a
will.
question, sir.
Yeah, please go ahead.
क्वालिटी फैक्टर जैसे हम लोग निकालते हैं सीरीज RL सर्किट में, ठीक है,
हाँ, ओके।
और ड्यूटी फैक्टर निकालते हैं आपका पैरेलल RC सर्किट में। तो इसमें तो सर सीरीज में दिया हुआ है RC सर्किट।
हाँ, इसमें RC सर्किट सीरीज में दिया हुआ है, तो यहाँ पे हम लोग कुछ भी निकाल सकते हैं, क्वालिटी फैक्टर भी निकाल सकते हैं, डिसिपेशन फैक्टर भी निकाल सकते हैं, राइट। उससे कोई बड़ी बात नहीं। लाइक डिसिपेशन फैक्टर ये हो गया, क्वालिटी फैक्टर इसका इनवर्स हो गया, 1/j ओमेगा C2R2, इजंट इट?
ओके सर।
लाइक सीरीज सर्किट का भी हम लोग डिसिपेशन फैक्टर निकाल सकते हैं। जनरली हम लोग निकालते हैं क्वालिटी फैक्टर जस्ट टू आइडेंटिफाई द क्वालिटी ऑफ द सर्किट, what how better it is, right? Like if let us say we have R and J omega L, so इससे कंफ्यूज नहीं होना है। अगर ऐसा रहे J R plus J omega L, पहला तो सीधा tan थीटा निकालने का है, tan थीटा इज इक्वल टू J omega L by R। यही हो गया क्वालिटी फैक्टर, यही हो गया क्वालिटी फैक्टर। और डिसिपेशन फैक्टर हो गया 1 by क्वालिटी फैक्टर इक्वल टू R by J omega L, तो माइनस R by J omega, R by माइनस J into R by omega, है ना। सो दोनों हम लोग किसी भी सर्किट में निकाल सकते हैं, कोई प्रॉब्लम नहीं।
ठीक है सर।
ओके, चल। So yeah, so next problem was, yeah, we needed to find out the voltage across this branch. Okay, so the concept of this kind of circuit is, why this kind of circuit is generally designed, which I was telling earlier, that very minimum voltage drop should happen at V2, because when we are tuning it, it may happen that V2 can be, all C2 and R2 can be tuned in such a way that we do not get proper balancing, and at such a high level of voltage it is very difficult to balance the bridge, and in such case very high amount of current could flow through this circuit, like that. Very high amount of current could flow through the circuit. So that is why we will see what we can do here. First, let us see with the problem. Let us calculate V2. So V2 will be equal to V into
R4 by R4
R4
जब V2 का निकाल रहे हैं सर
या V2 में R4 नहीं आएगा ना, C2 एंड R2 आएगा, राइट?
C2 आएगा, राइट सर,
यस यस।
बाई टोटल सम।
R2 plus 1 by j omega C2 divided
इसको
by,
मैग्नीट्यूड
मैग्नीट्यूड ही करना पड़ेगा, वो एंगल से नहीं होगा, है ना? तो डिवाइडेड बाय अंडर रूट R2 plus 1 by omega C2 square, sorry, no, R2 plus this R4,
R4 होल स्क्वायर
R2 plus R4 whole square plus omega C2 square, 1 by omega C2 square। ओके, और ऊपर में भी ऐसे ही करेंगे, इसका मैग्नीट्यूड निकालेंगे, V2 is equal to V into R2 square plus 1 by omega C2 divided by same value R2 plus R4 square omega C2। Now we will just plug in the values and we will get the magnitude here. So V is nothing but 4 kV, so 4000 into R2 and C2 we have calculated in the last part. So C2 is nothing but, first we need to find out the value of C2 is equal to C1 into R3, C1 into R3, so 1 microfarad into R3, 170 ohm divided by R4, which is 400 ohm. Okay, so we can calculate this value, 170 by 400. So 0.425 microfarad, that is the magnitude of C2. Now we need to find out the value of R2 because R2 was also unknown. So R2 is equal to R4. R4 is nothing but 400 ohm into C3 by C1. So C3 is 0.9 and C1 is 1. So 0.9, so it will be 360 ohm. So R2 and C2 we know here. We just need to plug in here. R2 is 360 square plus 1 by 2 pi into 60 into C2 is 0.425. Divided by R2 and R4. So R2 is R4 is 400 and R2 is 360. So 760 square plus 1 by 2 pi into 60 into 0.425 into minus 6. So this will be pretty tricky calculation. You just need your calculator here. You just plug in all those values and calculate. So you calculate on your own, but whatever you will get, the value will be equal to nothing but, I am just writing the value, that is 254.5 volt. So see, this voltage drop is 254.5 volts. So this is very small compared to 4 kV, 4000 volt, and here the drop is happening almost 255 volt. So rest of the drop will be here. Because this R4 is generally fixed in this kind of circuit, right? So sharing bridge is designed as that R4 will have the, you know, mostly or maximum drop there, and so that we will get the, you know, where even if you vary this R2 and C2, you will not get much large current flowing in the circuit, right? So that is why this kind of bridge is generally used in high voltage conditions, right? Any doubt in this part?
No, sir.
Okay, great. So let us move on to the next part, the next question. Mm, So we have given as a power factor of the coil is equal to 0.15. Okay, we are given with power factor. We need to find out the quality factor as well as dissipation factor. So since in this question it is mentioned as coil, it must be combination of resistance and inductance. Okay, now how to calculate quality factor? Quality factor nothing but, I told you, it will be tan theta, and theta is nothing but power factor, angle, and power factor is given. So what we can do, we can take inverse of it. So what we can write, tan into cos
Inverse theta.
inverse 0.15, and whatever will be cos inverse 0.15, that will be, if that will be the angle, and if you take tan of that angle, you will get 6.6. So the quality factor of this circuit is 6.6. Now we want to find out the dissipation factor of this circuit. That is nothing but 1 by quality factor, nothing but 1 by 6.6. So it will be equal to 0.15. So this is dissipation factor, this is quality factor. You just need to focus on the tan theta, how to get the value of tan theta. Then you can get all the values, whichever is asked in the question. Okay. I hope that clears the doubt related to quality factor and dissipation factor.
Okay, sir.
Okay, great. Now let's move on to the next question. Okay. So here again, an AC bridge is given, and we need to find the dissipation factor and quality factor, right? So let me draw the bridge here. This is R1. This is C4 and R4. Another have a coil, that is L2 and R2. And the last branch has only resistor. Okay. So are you able to recognize which type of bridge is this? What is the name of this bridge? If you have gone through the lecture.
AC bridge.
Yes, yes, it is AC bridge. The type of AC bridge like VN bridge or Anderson bridge or Steiner bridge or anything that must be taught in the lecture
Yes.
or similar to any bridge.
अभी तो याद नहीं आ रहा।
Okay, no problem. But it is basically more alike Anderson bridge. If you go and see, if you simplify Anderson bridge, you will observe this bridge. Okay. There was,
Okay,
you
okay,
know,
sir.
one a star delta conversion was also there. But after conversion and simplification, you see that that bridge will turn into this kind of circuit. So here we need to find out the quality factor in C4R4, which is variable. So in this part, we need to find out the quality factor, sorry, dissipation factor on anything. And here L2R2, you need to find out the quality factor. So that is why you were asking, right, Niranjan, that in coil, why generally we calculate quality factor, and in combination of capacitor, why do we calculate dissipation factor? So that is not any, rule of thumb that you need to find this kind of thing. Generally, in coil, people used to asking this question, but you can find anything. If you are able to find quality factor, you can find quality factor in any of the circuit. Okay, so
Yes, yes, sir.
that's yeah. So that should not be issue, right?
Okay, sir.
Yeah. So what is given in this problem, that this dissipation factor is given as 0.16. Sorry. We need to find out this quality factor. Okay. So what to do here? What should be, most efficient way to calculate quality factor here? Or, you know, find out the relationship between this branch and this branch directly. So we know that Z2, Z4 will be equal to Z1, Z3. And this equation has two components. One will be, magnitude, other will be angle. Or if you go in polar way, uh, sorry, in Cartesian way, you will have real and imaginary term, which will be bit hectic. Why? Because let me tell you, this is R3, right? So Z1 and Z3 are R1 and R2. Okay. Z2 and Z4 does have, AC components, and it will have angle. Let me turn on the light. Yeah. So Z2 and Z4 has AC terms, and we need to focus on this AC term. So the best way, or since we are given as this dissipation factor, it means indirectly what we know. We know the angle between R4 and C4, isn't it?
Yes.
We can easily calculate the angle between R4 and C4. That is nothing but 0.16 is nothing but dissipation factor, which is nothing but inverse of quality factor, which is nothing but 1 by tan theta. And in series RC circuit, tan theta will be equal to 1 by j omega C4 R4, right? Which is x by r, and x is nothing but 1 by j omega c, and r is r. So 1 by j omega c4 into r4. I hope it is clear till now.
Okay, sir. Clear, sir.
Okay, great. So now tan theta we can calculate from here. Tan theta is nothing but 1 by 0.16, right? From this expression, from 1, and it is nothing but 1 divided by 0.16, 6.25. So we know the angle of this. Angle of Z2 is, it is cos theta equal to tan inverse of 6.25. What will we calculate? 6 point
80.90.
80.9 exactly. So theta is nothing but 80.9 degree. So we know the angle of Z2 80.9 degree. If we can find the angle of we found angle of Z4, not Z2, of this branch. Z4 is 80.9 degree. If anyhow we calculate the angle of Z2, then we will be able to solve this problem. Okay. So how to calculate the angle of Z2? So since this expression is valid at any time, we can write in terms of angle, which will be theta 2 corresponding to the Z2 impedance plus theta 4, which is corresponding to Z4. Since impedance are in multiplication, angles will be in addition. Okay. If they would have been
Right,
in
sir.
division, that would have been in subtraction.
Subtract.
Which, yeah, and it will be equal to theta 1 plus theta 2. So since both are real, so all of them will be equal to 0. Since no imaginary terms are there, so tan theta is equal to 0 by R3 and 0 by R1. So both are 0, isn't it? Let me write it. 0 by R1 and here 0 by R3. So it will be 0. Now we are left with only angle theta 2 plus theta 4 is equal to 0, which will be angle of theta 2 is equal to minus of 80.9 degree. So theta 2 angle also we got to know with the help of angle equalization. So that theta 2 now, since we know, so what we can do, we can directly take tan theta and we can directly tell the quality factor, right? So again, tan theta 2 is equal to tan of minus 80.9, which will be again equal to, minus 6.25. And minus is nothing in terms of quality factor or this dissipation factor. So you can say that it is 6.25. So in this circuit, both the quality factor of both the branches are same, isn't it? Of both R4C4 and L2R2. So if, like, it is another way to memorize that if there are two bridges which have only resistive parameters and other two branches, diagonally opposite, which are going to multiply with each other, they have one capacitance in series with resistance, and other branch have, inductance in series with resistance, then the dissipation factor and quality factor of both the circuits are going to be same. So if you are, preparing for some other exam where you have to quickly find out the solution, and this kind of a statement is given, that power sorry where is, yeah, that this dissipation factor of this bridge C4 and R4 are given, you need to find out the quality factor. So you just immediately just see the nature of the circuit. If it is connected in this fashion, then you just take the inverse of dissipation factor, because dissipation factor of Z2 is equal to dissipation factor of Z4. You just can directly write it down. Okay. So I hope now all the concepts related to quality factor and dissipation factor must be cleared. If any final doubt is there, we can discuss on it. Or I
सर
hope,
यहाँ पे नेगेटिव
yeah.
साइन क्या है?
So
इसमें जो नेगेटिव साइन है उसका
ये negative sign ये just indicate कर रहा है कि there is capacitor, sorry, there is one in, if one branch have a capacitor and resistor and other branch has a inductor and resistor, so dissipation factor magnitude is definitely going to be same, but there should be
Yes, sir.
some indication that both branches have opposite nature of elements. One must have inductor and other must have capacitor. So that is why this negative sign is coming here, because had there been any similar nature of elements like inductance and resistance, and on the other hand also inductance and resistance, then it would have been in terms of positive. But here it is indicating that one branch has the combination of resistance and capacitance, and other branch has the combination of resistance and inductance. So that is why this negative sign is coming here.
Okay, sir. Clear, sir.
Okay. But there is nothing like negative quality factor or dissipation factor. So please be careful about that. If you get some numerical answer type of question, so please do not enter negative magnitude there. Okay. So these were all the questions which are enough to solve the week 5 assignment. All the problems that are provided in week 5 assignments are covered in this today's problem solving. Now we have some time left, so we can discuss some topic which were discussed in lecture, so that it will further clarify your doubts. So those kind of circuits are a bit tricky, where you need to simplify it with delta to star conversion and a star to delta conversion. So let us see those circuits, what kind of these circuits are there and how to solve it. Okay, but any doubt related to week 5 assignment we can discuss, because I have already solved and discussed all those problems. So
सर ये आप बोला था सर पिछला वीक में कि वो एक टॉपिक छूट गया था ना, उसका टाइम नहीं था हम लोग के पास, तो बोले थे कि अगला में डिस्कस करेंगे।
ओके, कौन सा टॉपिक था? एक्चुअली आई फॉरगॉट दैट टॉपिक।
देखना पड़ेगा सर हमको। लास्ट
let me
लास्ट क्वेश्चन था सर।
oh, with that lengthy resistance combination, right?
यस सर, यस सर।
हाँ हाँ। So actually जो that was on, let me open it. Yeah, so that was Kelvin-Warley potential divider. I hope
यस
that
सर।
was the circuit. Yeah. So yeah, so actually there is nothing much to discuss. I went through, so it is just the switch through and connect phenomena, where you can vary the resistance of the last circuit, because the role of potential divider is to provide the potential difference, or provide the voltage value corresponding to the resistance connection in the circuit. So if you have many resistance connected in series like that, and if you are going to have multiple, because one potentiometer will have two those switches, so where do you connect so that you get the desired amplitude of output voltage? So that was the purpose. So let me draw this circuit. So it is given like that. If you have gone through the lecture, let me draw the circuit. So one example must be discussed by the professor in this fashion, or not this fashion. They are connected like this. So there are 11 resistors were connected in this fashion. Three, 6, 7, 8, 9, 10, 11. So 11 resistors are connected here. Okay. And supply voltage is given as V in. Okay. And we have another circuit or another combination of resistance in the similar fashion with 10 resistance. 3, 4, 5, 6, 7, 8, 9, 10. So in the output side, we have only 10 resistances, and this value of R1 and R2 are such that R2 is equal to R1 by 5. Okay. Now, this mechanical coupling or these throw switches are done in such a fashion that we have 2 point of contacts. One is after the 8th resistance on the first side, so this one is 8th. Okay, so here one throw is made like that, and another, this is connected to this branch, and another throw is made to resistance after 6, so 6, 7. So this is 6, right? Like that. Okay, so now we need to find the value of V2 or of the output V out corresponding to the 6th resistance. So one is connected to here and other is on the ground. Okay, so we need to calculate this voltage, output voltage. So it will be nothing but, kind of voltage divider circuit. But how do you calculate this? It is just looking like it is intimidating, but it is not that much intimidating if you just simplify it. So all these resistances are R1. So how do you solve it? Because you know the potential divider rule or voltage division rule, how to apply them. And it is nothing but Kelvin. Its name is, let me write, Kelvin Waverlet potential divider. Okay, so its role is to, just provide the voltage across the particular switch throw. So we have connected two throws of this mechanical coupling switches. One is connected after 6th resistance of the first branch, and other is connected to the after 8th resistance of the first branch. Okay. Now, if you want to calculate here, this R1, this 2R1, look carefully here, this 2R1, R1 plus R1, they are in parallel with this 10R2. I hope you are able to observe it, right?
Okay, sir.
Okay. So this 2R1 is in parallel with 10R2. Okay, that is one thing. But first we, because these two R1 are connected in parallel to 10R2, but again there's another switch which is connected to after 6R2 on the output side. Okay, so we have total two stages. Okay, and if you have some voltage in your mind that how much amplitude do you want on the output side, you can connect P2 or P1. Let us call it P2 and P1. You can connect P2 and P1 in such a fashion that you get the value whatever is required. So if 10R2 is equal to 2R1, okay, we have 10R2 is equal to 2R1, then equivalent resistance of the first stage will be 9R1. Okay, if this first stage, this is the first stage, and this we are calling as a second stage. Okay, because these two R1 are getting in parallel with the next stage or second stage 10R2. Hence, there are 9R1 that are left. So equivalent resistance of the first stage, let me write. So equivalent resistance of first stage is nothing but total 9R1, okay, plus 2R1 in parallel with 10R2, isn't it? I hope it is fine till now. Okay.
Right,
If there,
sir.
yeah. Now this 10R2 is nothing but is equal to 2R1 because R2 is equal to R1 by 5. So is equal to 9R1 plus 2R1 in parallel with 2R1, and which will be further is equal to 9R1 plus 2R1 in parallel with 2R1, which will lead to R1 only. 2R 2
R1.
2 and 2 ohm is parallel with, then it will lead to 1 ohm. So similarly, 2R1 and 2R1 are in parallel, so 1R, which is nothing but equal to 10R1. Okay,
Yes,
right.
yes, sir.
Yeah. Now we want to calculate output voltage. We wanted to calculate this output voltage, and this will again will have two components. One will be V out. V out will be equal to V out 1 plus V out 2. First output because of first stage, that is why I have denoted with 1, and second with the second stage. So the first stage will be equal to V out 1 will be equal to V in into this 2R1 in parallel with 10R2 because that will be the equivalent resistance of the first stage. So V in into 2R1 into parallel with 10R2 divided by 9R1 plus 2R1 parallel with 10R2. The same thing whatever we just calculated here, that will be the V out of the first stage. Now the second stage will have what they will have? They will have how much this 4R2, isn't it? 4R2 by 10R2. So one
Yes, sir.
is whatever has come out here, V out 1. So V out 2 will be this V out V in into, sorry, V out 1 into 4R2 divided by total is 10R2. So V out 2, let me zoom it out. So V out 2 is nothing but V out 1 into 4R2 divided by 10 odd. So it is a straightforward V output 1 into 4 by 10. So now the total output voltage will be V out 1 plus 4 by 10 V out 1. So that will be 14 by 10. So 1 by 4, 1.4 V out 1. So now we just left to calculate this V in into 2R1 parallel with 10R2 divided by 9R plus 2R parallel with 10R2. So as we have already calculated, this value will come out to be how much? 2R in parallel with 10. So it will be R1 V in into R1, right? 2R1 parallel with 10R2, that will lead to R1. Now 9R1 plus 10, 9R1 plus R1. So V in divided by 10, because R1 and R1 will get cancelled out, right? So V out 1 is V in by 10 and V out 2 is nothing but 4 by 10 into V out 1. So total we have V out is equal to V out 1.4 V out 1 and V out 1 is V in by 10. So we can write 1.4 into V in by 10, and which is nothing but 0.14 V in, isn't it?
Right, sir.
Right. So this is the value, or this is how, because see, we have two stages with lengthy combination of the resistance. So we have to go a step by step. So wherever it is getting connected, this P2 and P1, we have to focus and we have to calculate V out 1 from the V in. We have to go from this side, from input side to output side. So input side is V in into this 2R1, which is in connected with parallel in the next stage resistance, and we can appropriately apply the voltage division rule. After that, we calculated the voltage at the first stage. Now we are ready to go on the next stage, and next stage will be again voltage division rule applied on the circuit connection, depending on the circuit connection. Okay.
Okay, sir.
Okay. So this is how you calculate it. And I hope you were able to solve the question of the assignment.
Yeah, yes, sir.
Okay, okay, great. So this is related to the what is the name of this potential divider? Kelvin-Warley potential divider. And in exam also, please be very careful while you are getting this kind of circuit. And there are some shortcuts also which has been demonstrated in the lecture by professor. So on the basis of where the switches are getting connected, P1 and P2, you could directly write the output value. If you go through the notes, also you could see that V out is nothing but some kind of P1 or factor of P1 into V in plus factor of P2 into V in. If there are three stages, you could go till P3 and P4. So like that. So there could be multiple stages, but this is the fundamental. It could be 4 stages, 5 stages, but you got the basics of this, right? How to calculate first stage, then after that you could go further on. Okay. Okay. Now we were going to see this topic. So one BN bridge is left, which in the problems were not given in this week assignment based on BN bridge. So you may expect in the exam to calculate the circuit, AC circuit based on BN bridge. So let me draw here. It is very important bridge. So it is like that. One again, resistance and capacitance are connected in parallel with Okay, so this is how they are connected: R3, R4, R1, C1, R2, C2. Okay, and they are given with an AC sinusoidal supply. Okay, so these two adjacent branches have resistance and capacitor connections only, one in series and other in parallel.
वेन ब्रिज में मतलब एक आपका पैरेलल में कनेक्शन रहेगा और एक सीरीज में रहेगा क्या सर? दो
एग्जैक्टली,
ब्रांच
बट
में।
हाँ, दोनों में रेजिस्टेंस एंड कैपेसिटेंस का ही कनेक्शन है, एक में सीरीज एक में पैरेलल, दोनों में रेजिस्टेंस एंड कैपेसिटेंस का कनेक्शन रहेगा, और लेफ्ट दो ब्रांचेस में ओनली रेजिस्टेंसेस विल बी देयर. Okay, yeah, so now again, how to balance it? So it is pretty straightforward, and here you could calculate, frequency of this circuit at balanced condition. So R4 into R1 and C1 are in series, so R1 plus 1 by J omega C is equal to R3 and Z2 are in combination. So Z2 you can take it on the other hand side, because if resistance and capacitance are connected in parallel, then what you can do, you can write R1 plus 1 by J omega C1 into 1 by Z2 is equal to R3 by R4. I have just simplified it so that we could use it in better format. Now
वाई का
Z2
फॉर्म
is,
में भी,
sorry,
वाई का फॉर्म में भी लिख सकते हैं ना सर ये?
हाँ exactly, y के form, y 1 by Z2 is nothing but y2, isn't it? So 1 by Z2 is equal to y2. Let me write it. Now they are in parallel, so we can add, that will be like 1 by R2 plus J omega C2. Okay, so this is how 1 by Z2 we can write: R1 plus 1 by J omega C1 into 1 by R2 plus J omega C2 is equal to R3 plus R3 by R4. Okay. Now, if we can only focus on, real term or imaginary term, so we will do a step by step. So first we will focus on first we will segregate them. So nothing, R1 by R2 plus 1 by J omega L1 R2 plus R1 J omega C2 R1 plus J omega C2 by J omega C equal to R3. Now, this imaginary term will be cancelled out. Okay. Now we have only two imaginary components. These two are imaginary components. Okay. And we have frequency terms in these two components only. So what we can write, like 1 by J omega L1 R2 plus J omega C2 R1 is equal to 0, right? Now we further simplify it. So we will get J square omega square, isn't it? And okay, let it go step by step. So J omega C2 R1 is equal to minus 1 by J omega L1 R2. Okay. This J, if you take in numerator, this negative sign will become positive. So J by omega L1 R2. So this J and J will cancel out, and this omega will come on this side. This will be omega square is equal to 1 by L1 C2 R1 R2. Sorry, L1 not C1. C1 only, right? Yeah, L1, no L1, it is C1 only. Because in this circuit only capacitor are there. So there is no point inductor is coming in this circuit. So everywhere it is C, not L. It is just looking like L, but it is C. So now omega is equal to under root 1 by C1 C2 R1 R2. So the frequency is dependent on the C1 C2 R1 R2. So these two branches will have the dependency on the frequency. These two branches does not have any role in determining the frequency of the circuit at balanced condition. Okay. So this
Yes, sir.
bridge, why do we use this bridge? Do you have any idea? Just to calculate the frequency of any unknown frequency. If you do not know the frequency of any circuit, then you can use this bridge. Okay. We do not measure or we do not use this circuit to know the value of unknown capacitor. For that, other bridges are already there. Okay, so this bridge is a standard to measure the frequency of the circuit, which is very easy and very straightforward. So main bridge
Yes.
objective is to measure
Frequency.
unknown frequency.
Un-
Yeah. Okay. So I hope it is
okay.
clear to you. Yeah.
Clear, sir.
Great. So now we are done with this. So next is a star delta, which is a bit confusing. So let me draw one circuit, which is nothing but Anderson bridge. Let me go with that. So here, how they are connected. R1, one resistance, another branch has inductance and resistance that is unknown, Lx and Rx. Okay. It has R4, it has R5, it has R1. Now here, in series with galvanometer, we have connection like this. C3, R3, and here deflection will. Okay. So this circuit looking like a bit complex. Okay. Some AC supply is there. So, but we are used to solving a straightforward circuits where all the branches are diagonally opposite connected. So here also we can make like this. We just need to convert this delta circuit parameters, which you can observe it here. We can, if you convert it into a star, then you will have the real circuit. You will have it as a earlier circuit or conventional circuit. Okay, so uh, let me write the value of these parameters. So these are ZA, ZB, and ZC we can call. So how they will be connected finally. So R1 and ZA will be like that, isn't it? And ZC will be come here. Lx and Rx. And here it will be R4. And one ZB will be left here in series with galvanometer. Okay. So this is how, if you solve the circuit, you will get. Okay. I hope it is fine till now. Now here, ZB, is considered as a internal impedance of this detector.
Yes, sir.
So we do not need to bother about ZB. We just need to calculate ZA and ZB. That will be sufficient for us. So how to calculate ZA? So ZA will be corresponding to R3 and R5. ZA is placed in corresponding to R3 and R5. And from delta to star, what we do, we multiply those corresponding parameters, R3 and R5, divided by summation of all those three impedances. So R3 plus R5 plus 1 by J omega C3. Okay.
Yes, sir.
So we are done with ZA. Now we need to find out the value of ZC. Okay. So ZC will be again R5 and C3. It is connected across the R5 and C3. So R5 into J1 minus J by omega C3, we can write like that. And R3 plus R5 minus J by omega C. Okay. This much is
Right.
the value of ZA and ZC. And now if you equate it, because we want to find out the value of Lx and Rx, so for that we can write Zx into Zc is equal to R4 into Za. Okay. Now Zx,
सर इसमें
yeah,
जेड में
हाँ, ZA में क्या, ZA में ये है R3 R5 R3 माइनस साइन यू आर आस्किंग, हाँ, सो सी माइनस ही नथिंग, ये J अगर ऊपर जाएगा तो माइनस हो जाएगा, राइट?
ठीक है सर,
ये J अगर यहाँ पे ऊपर गया तो माइनस हो जाएगा.
ठीक है सर, ठीक.
Okay. So Zx we have J omega Lx plus Rx. Zc we have, Zc is like that. So we can further simplify, but it's better minus J R5 divided by R3 plus R5 omega C3 minus J by omega C. Okay. And is equal to R4 into ZA. ZA is again R3 R5 divided by R3 plus R5 minus J by omega C. So one thing is going to get cancelled, that is the denominator part. Okay, so this part will be cancelled. Now we are left with only J omega Lx plus Rx multiplied with minus J R5 by omega C3 is equal to R4 R3 R5. Okay, that's all. Now we can make real part as well as imaginary part. On the left hand side, if you multiply this J and this minus J, that will be minus J squared, that will be 1. So omega Lx R5 divided by omega C3. Okay, this is one term, plus other term is minus J Rx R5 divided by omega C3. If you equate, it will be R4, R3, R5, isn't it? Now we are left with this imaginary term, which is not going to give you frequency of this circuit, because imagine we do not have any imaginary terms on the right hand side. Okay, so what we are going to equate? We are going to equate real terms. So this omega and omega will be cancelled out. So Lx R5 divided by C3 is equal to R4 R3 R5. So Lx will be equal to C3 R3 R4 R5. Yeah, five terms will be there divided by R. So this R5 and R5 will be cancelled out. So only three terms. So Lx is nothing but C3 R3 R4. So let us go back to the circuit. Lx is nothing but C3 R3 R4. Okay. What about Rx? What can we tell about Rx?
Rx will be 0, sir.
Rx we can tell 0. Yeah, Rx we can say 0. But ideally, Rx will not be 0. Practically, Rx will not be 0. Here from the equation, we can say 0, but Rx will have one component along the ZB. But yeah, from this balancing, we can tell Rx is equal to 0. Okay. So this is how we solve this kind of circuit, and we calculate the impedance of the unknown parameter. And here Rx will be very useful.
So,
Okay. So this is
yes, sir.
the standard bridge of Anderson, and this is how we solve it. So the important part were only to convert delta to a start. The rest was very, very easy, right?
Yes,
After
sir.
that, it's nothing but the balancing equation. Now,
Yes, sir.
other bridge is the other way around, where we need to convert from a star to delta. So that bridge is known as, I think Maxwell bridge or something. Mm. So if you see, like, you are getting, elements connected in fashion of a star or delta, it's better to bring them in the form of a standard bridge and then further you solve. So this is all regarding to bridges, like Anderson bridge, Maxwell bridge, Sharing bridge. Sharing bridge is for very high voltage, right? So as I solved in problems also, so the Z1 is fixed and Z2 is variable. Like, where is the problem where we solved? Yeah. So this was the circuit of sharing bridge. Here Z1 is fixed, Z2 is variable, where, sorry, Z1 and Z2 are getting, yeah, so what can we vary here? We varied what we required R2 and C2. So R2 and C2 we can design such that very minimal drop happens across the second branch. Okay. So
Yes, sir.
this is all regarding bridges. I don't think anything is left from the bridges. I hope you will be able to solve all the problems based on bridges.
Yes,
Maxwell
sir.
bridge is a straightforward, that is multiplication. So yeah, I think that's all for today. today's session? Any final doubt before winding up?
No, sir.
Okay, then that's all for today. Thank you very much for joining, and I hope you will be able to solve all the assignment problems. This week assignment problem is very straightforward, and all concepts were discussed in today's session. So I hope that should be fine. Okay, thank you, Niranjan.
Sir.
Thank you so much. Yeah,
Good night, sir.
bye. Good night.